We spend a lot of time talking about how medicines get into our bodies and do their thing. But what about the end of the story? Let's dive into a drug's exit strategy, that absolutely crucial final chapter of its journey.
Think about it. You take a pill, it does its job, you feel better. Seems pretty simple, right? Well, not so fast. What happens after the magic happens? Turns out getting that medicine out of your system is just as critical as getting it in. And believe me, it's a process with some very, very strict rules.
All right, so where does this great escape actually take place? Our bodies have this amazing built-in cleanup crew, a real powerhouse organ that's in charge of showing these drugs the door. And yep, that powerhouse is the kidney. It doesn't matter if the drug is still in its original form or if it's been broken down into little pieces, what we call metabolites. The kidney is the main exit ramp off the body's superhighway. And this isn't just some simple flush, okay? The kidney has this incredibly precise three-step process. First up is glomerular filtration. That's kind of like the initial security screening. Then you've got tubular secretion, where it actively boots certain things out. And then there's diffusion, where some stuff can actually slip back in. It's a super sophisticated, highly controlled system.
Okay, so we know where the drugs make their exit. But the next big question, the really crucial piece of the puzzle, is how fast do they leave? This is not random at all. It's a really carefully timed process that follows a specific set of rules we call reaction kinetics.
So the central idea here is something called the order of reaction. And really, all it describes is the relationship between how fast a drug is eliminated and how much of it is in your body. The big question is, does the drug leave faster when there's more of it around? And the answer to that question splits drugs into two totally different camps.
And those two camps are what we call first-order and zero-order kinetics. Think of them as two completely different rule books, two different exit strategies. And let me tell you, understanding the difference between them is absolutely key to, well, pretty much all of modern medicine.
Okay, so here's the absolute heart of it. With first-order kinetics, the body gets rid of a constant fraction or percentage of the drug over time. So let's say it eliminates 50% per hour. If you have 100 milligrams in your system, in that first hour, poof, 50 milligrams are gone. Now you only have 50 left. In the next hour, it clears 50% of that, so only 25 milligrams. See how the amount changes? Now, zero order is totally different. It clears a constant amount. It doesn't care how much is there. It's just going to remove, say, 10 milligrams every single hour, period. The rate is totally fixed.
I love this analogy for first order. It's like a crowded stadium emptying out after a game. Right at the beginning, when it's packed, people are just pouring out of the exits, right? It's a rush. But as the crowd thins out, the flow of people leaving slows way down. The rate of exit is totally proportional to how many people are still inside. And that's exactly how most drugs work.
And if you plot this on a graph, you get a really distinct visual signature. So what we're looking at here is drug concentration over time. See how the line starts off super steep? That's when the concentration is high and the drug is leaving fast. Then, as the concentration drops, the line starts to flatten out. That downward curve, that's the classic telltale sign of first-order elimination. All right, now let's flip to zero order. The perfect analogy here isn't a bunch of open exits. It's more like a single-file security line at the airport. It doesn't matter how long that line gets, right? Only one person can get through the scanner at a time. The exit rate is totally constant. We say the system is saturated. It's already working at maximum capacity. So, what does the graph for zero order look like? Well, it's completely different. Because a fixed amount is getting removed every hour, the concentration drops in a perfectly straight, predictable line. It's just this constant downward slope. And that has some really big consequences. So, okay, we've got these two different rule books for how drugs leave the body, but why does any of this actually matter? Well, in the real world, in actual medicine, understanding this difference is absolutely critical for doctors to prescribe drugs safely and effectively. And this whole idea of kinetics leads us directly to one of the most important concepts in all of pharmacology, the half-life. It's a simple idea, really. It's just the amount of time it takes for the drug concentration in your plasma to drop by exactly 50%. And this is where it all clicks together. For those first-order drugs, the stadium emptying out, the half-life is constant. It's predictable. You can count on it. But for zero-order drugs, that single-file line, the half-life is not constant. It actually changes depending on the concentration. This makes them way more unpredictable and, frankly, a lot trickier, even dangerous to dose correctly. I mean, this one number, the half-life, is unbelievably powerful. It helps doctors figure out basically everything about dosing. How long will a single dose work? How often do you need to take it? How long is it going to take to reach a stable, effective level in your body? It's all connected to that half-life.
Yeah, let's dig into that last point for a sec. If you're taking a medication every single day, how long does it actually take for it to build up to a consistent, effective level in your body? We call this reaching a steady state.
Well, there's a really simple and powerful rule of thumb that doctors use all the time. It takes about 5 half-lives to reach that steady state. Basically, after about 5 half-lives, the amount of drug you're taking in with each dose roughly equals the amount your body is clearing out. And that's when the levels in your blood stabilize. And the math behind it is actually pretty cool. After 1 half-life, you're at 50% of that steady level. After 2, you're at 75%. After 3, 87.5%. You see the pattern? By the time you hit 5 half-lives, you're at a whopping 96.875% of the final concentration. For all practical purposes, you're there. You've reached a steady state.
Okay, so let's wrap this all up. What are the big takeaways? First, the kidney is the main exit route. Second, drugs follow one of 2 rule books to get out. First order, which is a constant fraction, or zero order, a constant amount. Third, those rules determine a drug's half-life. And finally, that half-life is pretty much the master key that dictates how doctors can dose a drug to be both safe and effective.
So the next time you take any medicine, you can ask yourself, what's its exit strategy? Is it leading in a big rush, like that crowd pouring out of a stadium? Or is it waiting patiently in a single-file line? The answer to that question isn't just a fun thought experiment, it's a fundamental principle that makes modern medicine work.